So I start, right? I'm trying to give a brief summarize of the basics of deep learning, and I try to be short and not enter much into the details. So if you want to enter into details, well, maybe later we can discuss for some time, or just I can give you some references, or you can find them online. Okay, so so essentially deep learning refers to machine learning with neural networks which are deep in connectivity. In this case, I show an example of a fully connected neural network in which you have, I hear some, okay. Do we all of us has the mic muted? Okay. Okay, now. So in this case, you have an input layer here with some numbers of neurons. Then you have, in this case, two hidden layers, which are fully connected. So every neuron is connected to all of the neurons of the next layer. And then you have the output layer. This type of fully connected neural networks were typical in the 90s. And one of the problems of these neural networks is that the number of connections that is just written here, so the number of weights represented by these arrows is the number of input neurons in the input layer times the number of neurons in the hidden layer number one, plus the same for the two hidden layers, plus the same for the hidden layer to the output, exponentially increases when you increase the number of neurons in each layer, and you also increase the number of layers of the of connectivity. So during the 90s and the first years of the 2000, this was a problem, and it was suggested that there might be different options to overcome these difficulties, and one of them that was proposed by Jan LeCun, who was now the chief director of the machine learning division of Facebook, is that is to use convolutional neural networks. In this case, you have the input layer, and here, and from the input layer, you generate a hidden layer, which is computed by convolutions with kernels of different height, width, and depth. One of the advantages of this is that you are now sharing the parameters, so you are not connecting every single neuron on the hidden layer to every single neuron in the input layer, but you are connecting them with shared weights. So that has an immediate advantage in that the number of connections, the number of weights that are active is exponentially decreased. And then you can connect many of these convolutional layers together to end up with, I mean, the typical neural networks that convolutional neural networks that we have now available. So here I explain the basic ingredients of convolutional neural networks. So here you have an input plane made of 32 by 32 by 3 pixels, so 32 in the horizontal direction, 32 in the vertical, and 3 in the channel direction. And you get, I will show now later slide in which this is much more clear, but you just get the values of the hidden layer by just convolving this input image with a certain kernel of some size. In this case, it's a small small size kernel of the order of 5 or 10 or something like that. And then when you convolve this kernel through all the input layer, you get the hidden layer. After that, like in a normal neural network, you have the convolution, and then you apply a nonlinear function, in this case f, which makes all neural networks nonlinear. So that's the advantage of neural networks over any linear approach to machine learning. Here you can see a much clearer representation of how a convolutional neural network works. Here you have the input, which is just a discretized input volume. Here you have the vertical direction, the horizontal direction, and the depth direction, or the channel direction. And then you convolve this input volume with a kernel. In this case, it's a small kernel of this size that is moved at every single point on the input channel, and then you generate a new point in the output channel, in the output layer. So this is how it works. So you start moving the kernel through the input, and then for each one of them, for each kernel, you generate a new output, and then you propagate this from layer to layer. Okay, this operation is just a linear operation, so it's just matrix multiplication, and that's the reason why we use GPUs to compute that, because GPUs are especially efficient in computing products, so linear operations in general. So that's the reason why you use a GPU for computing convolutional neural networks, because you gain a factor of the order of 10 or even more when you apply, as compared with a standard CPU. Then the kernel is, in principle, is shifted every single point on the input, but you can also shift that by a different amount of inputs, and it's this amount is called a stride, and then you get an output which has a different size of the input. Here is an example of how a stride works. Any question? Okay, so this is an example of how the stride works. So here you have the input channel, and this is convolved by a kernel of size 3. And then for every 3 numbers, every triplet, you get a new number, which is obtained by just multiplying the 3 input channels by the 3 values of the kernel. And then you move the kernel by just one quantity, and then you get the output. Okay, you can also move the kernel by, in this case it's 1 by 1, then you can move it 2 by 2, and then the output has a different shape. In this case, you reduce from output 5 to output 3. Okay, and then you can play with the strides and the size of the kernel to adapt the input to the output. This equation relates the input, the size of the input with the kernel size, and with the zero padding, you can add zeros to the borders, or you can add reflection padding, and then to the stride. So this number defines the output volume, and then you can find the values of the stride and the padding if you want to keep, for instance, the input and the output size. Okay, another thing that is also interesting is with convolutions. In this case, it's a convolution with a 3 by 3 kernel, and then you can see how the kernel is moving throughout the input and generating the output. But we also use one by one convolutions. So instead of using, in this case, a 3 by 3 kernel, we use a 1 by 1 kernel, which seems a little bit strange, but this is a way of projecting a certain number of channels of input into a certain number of output channels. Okay, and we use that for some of the neural networks we have published to end up. So at the output of the neural network, we have, let's say, 64 channels, and then we want only one channel as an output. So then we apply a one-by-one convolutional kernel to combine all these 64 channels into only a single scalar.
So can you explain?
Yes.
Can I ask? How is the one-by-one convolution different than the non-convolutional neural network?
Well, in this case, this one-by-one convolution is just combining all the channels with a certain weight. So essentially, it's equivalent to a fully connected neural network, but with shared weights. So all the weights are shared between among all the neurons. So you don't have a different value of the weight for every neuron. So that's a very efficient way of reducing the number of channels.
All right, thanks.
Okay. So then after convolution, so if we only use convolutions, then the neural network is linear, and we don't want a linear neural network because we want to explain nonlinear things. So that's the reason why you need an activation function. In the past, followed by what we assumed that the brain was doing, we used things like sigmoid functions to activate the neurons. But this has a problem because a sigmoid function has a saturation, and then the derivative of the sigmoid function becomes really, really small when the activation becomes large. So that's the reason why a few years ago, people realized that if you use this rectified linear unit, which is just a very simple activation function, it's a nonlinear function because for negative values of the input, you get 0. But for positive values of the input, you get just a linear propagation. So this is a nonlinearity, and it has been tested that it works really nice. And the reason that it works is that the derivatives of the activation function here are constant. So you don't have the vanishing gradient problems in which when you backpropagate information from the output to the input to compute essentially the response functions, using sigmoid type functions, the derivatives become really small. With this approach, with this activation function, you don't get that problem. And so you can train really deep neural networks with hundreds or even thousands of layers. And essentially, this is produced by this rectified linear unit. Another interesting operation that people use in neural networks are the pooling operation. In this case, it's a way to reduce the size. Yes?
Can I ask a question concerning the previous slide?
Yes.
Could you mention again what is the basic motivation and what is the meaning of activation function again?
Yeah, okay, let me start. The activation function is once you enter into one of the neurons with the convolution of the previous layer, then you need, this is just a linear combination of the inputs, and then you apply a nonlinear function to that. Okay, so people used sigmoid type functions like the hyperbolic tangent and things like that, trying to mimic what the brain is doing. So if you have a very strong signal, the brain just saturates to, let's say, +1, or if you get the opposite, it saturates to -1. So that was the reason why people used hyperbolic tangents as an activation function, as a nonlinearity in neural networks. But this has the problem that the derivatives of the hyperbolic tangent when the input is very large is very close to 0. So neural networks are trained by just backpropagating, so computing response functions of the output to every weight on the neural network. And since the way the activation function is setting very small derivatives, this information cannot be back propagated very far into the network. So that's the reason why people decided to use activation functions that keep the gradients. In this case, this is just a linear function. So if the input is positive, the derivative of the response function is just 1. So you still propagate gradients back into the network from the output to the input. That was the main motivation for that.
Thanks.
Okay. So as I was explaining, if you want...
So, and then what does the 0 part do?
The 0 part is just introducing a nonlinearity in the problem.
But
so
it means that any negative input, no information back propagates from any negative input, right?
Exactly, yeah. So if you have an output and the output of the neuron is negative, then after activation, the neuron has a 0 at the output. And so you can have neurons that are completely deactivated during training, or they have to adapt so that the output is positive. And then you have a response. But this produces a nonlinear response of the neural network, yes. Okay. So in cases in which you have to pull information, spatial information from the images, like for instance, if you want to detect dogs in images, then you need to have a look at the image as a whole. Then for that reason, people use pooling operations, and which is essentially just decreasing the spatial sizes of the images. So imagine you have an image like this one, 224 times 224 times 64 channels in the third dimension. If you apply a pooling operation, then you reduce the horizontal and the vertical dimensions by a factor 2. And this means that you are putting spatial information into smaller scales at this in this part here. One of the most used pooling operation was the max pooling operation, which is also a nonlinear operation. So in this case, you want to go from this size to this size. So for each one of these 4 elements, you just put the maximum value. So in this case, it's 6. For this case, it's 8, and then 4 and 3 in this case. So you are reducing the size of the image, and you are also pulling spatial information into smaller and smaller scales of the image. This was typical in the first neural networks, in the first deep neural networks, because they were essentially made for classification. So if you want to, as I said, you want to detect a dog in an image, then you need to, the output is just 1 or 0 if there is a dog or not. And then you want to decrease the spatial information until you end up with just a single number. So that's a very efficient way of doing that.
To get to hear us, yeah.
Yes. Andres?
Yes?
But with this, you lose contrast. So you don't lose a lot of information with this? When you said that this one was for image classification.
Well, it depends. So if you want to do image classification, this is a very simple way of reducing the dimensions of the image. If you want to do image-to-image translation, then this is probably not something you wouldn't do. Okay, because you are reducing the size of the image.
Thanks.
Something you can do, and I will show you an example later, is to do a codification, so an encoder-decoder network in which you reduce the size of the images, but you also increase the number of channels available. So this spatial information is encoded into channels, and then you decode the image again by reusing the information on the channel. So it's a way to compress the image and just keep whatever is interesting for you. Okay, so another improvement that happened a few years ago was the concept of residual connections, and almost all the modern deep neural networks use residual connections. The idea is that deep neural networks is a collection of convolutional neural networks with some activation functions. But someone realized that it's good to introduce a shortcut of the input and then add that to the output after several layers. The reason for that is that when you are backpropagating, and then you are going through the network from the output to the input, and you find one of these residual connections, a large fraction of the gradients is just transferred directly through the identity connection. So you are computing the derivatives through this identity connection, and this is just transferred back to the network. And then you also take into account the derivative with respect to the weights of the convolutional layers here. This residual connection allow people to train neural networks of 1,000 layers without any single problem, because the gradients backpropagate with large amplitudes through the identity connections. And as I say, almost all modern neural networks have some kind of shortcut like this one to help in during the training. Okay, so convolutions not only reduce the number of connections, the number of weights, but it also allows, when you put many of these convolutions together and with reduction in size, like max pooling or things like that, or using different strides, it allows to view the image at different scales. So when you have an input, and then you apply the first convolutional layer with a small size kernel, let's say 11 by 11, then you detect your 11 by 11 kernels will be probably edge detectors or things like that. So it will focus on small scale details, and they will adapt to things that we often know, like, for instance, edge detectors or blob detectors, things like that. Okay, then this first layer will analyze the image at a small scale, and then you start max pooling or reducing the size with strides, and then the subsequent convolutional layers will start analyzing the image at a larger scale because you have reduced the size. So, for instance, it will analyze the image as a texture scale, and then the deeper convolutional layers will analyze objects at a much larger scale, and so on. The deeper layers will analyze the whole image as a whole, so trying to detect spatial correlation. And then at the end, for instance, you can have some fully connected layers, and then the output that predicts what you are seeing. Let's say, is it a dog, or is it a car, or whatever. So this multi-scale analysis is very interesting, and it's just a consequence of the fact that you are using convolutions and many convolutional neural networks, one after the other. The architectures that people are using now in convolutional neural networks is really hard to follow. So, I mean, you can have things like that, in which, as I mentioned before, you have an encoder part in which you take an image, and then you start decreasing the size of the image, but increasing the size of the number of channels, and then later you try to encode again the information into a large image. That's very similar to what we have for the convolution, for the multi-frame blind deconvolution approach. Or you can have things like that. This is WaveNet. This is the Google's generation of speech. So it's a convolutional neural network, in this case in 1D, which generates raw waveforms. So you generate the raw speech by convolving the input and then using different strides in this case. And then once you generate a new output, you move this structure one position to the right, and then you again predict. And I think this one is used now by Google to produce text-to-speech. Or you can have things like that in which you have not only connections, a direct connection between one layer and the next, but you also have skip connections between one layer and the following one, and to all of them after that. This is a way to quickly propagate gradient between the input and the output. So things like that. And things like this one that, I mean, it's hard to understand what is this doing, okay? So how do we train neural networks? It depends on what we want the neural network to do. For our cases, we are often interested in regression. So we often want to optimize the L2 norm of the difference between the output of the network and the training dataset that we have. Okay, so this is for images. In this case, it's a sum over the number of images and a sum over the every single image of the square difference between the output and the input. This is done through the application of the gradient descent. This is probably the simplest way of optimizing a function. But since we are dealing with millions or tens of millions or even hundreds of millions of free parameters, this is probably the only, so first order algorithms are probably the only way that we have to train a neural network at this moment. Essentially, you need to compute this quantity here. That's the gradient of the output of the merit function with respect to the parameters of the network. And then you multiply this gradient by some step size, and you just add that with a sign change to the current estimation of the parameters. So that's probably the most stupid way of optimizing a function you can find. These gradients are now computed at machine precision using automatic differentiation. And there are many packages for that. You can use TensorFlow, I use PyTorch, or you can use whatever. So there are a few of them following different philosophies, but nobody computes derivatives by hand. One of the really improvements in deep neural network was the fact that people realized that you don't need to use the gradient descent method to update the value of the parameters. People realized that you can use subsets of the input of the training data set, and once you have a subset of that, you can estimate a noisy version of the gradient, and then use that gradient with a certain step size to update the value of the parameters. So you do that for every batch in your data set. So imagine you have 1,000 examples in your training data set, and you have a batch size of 10. So then you repeat, you do 100 steps like this one per epoch, so per full data set. And this is proved to converge even faster than the full gradient descent. It has also some good properties. In this case, I show a movie as an example of how several different optimization methods based on this gradient descent, but with different ways of computing this step size, and how they converge to the solution. And you can find methods that are faster than the others. One of the problems with neural networks is that we are never in this situation in this. So neural networks are non-convex. And non-convexity is a problem because you can find situations like this one in which you have a global optimum, but then you have local minima in which you can, when you are optimizing the merit function, the loss, you can just stay there and never reach this point here. This was supposed to be a problem initially with deep neural networks because, for instance, you are training networks with 10 million parameters and you only use 10,000 training examples. This is something we are not allowed to do when we are at the university level, but that people use or try to solve problems like this without any problem. And one of the good things that was that neural networks at that time were successful in solving this kind of problem. So now there was an issue that why does this happen? Why do neural networks work when we are training with much fewer examples than needed, following the standard theory, especially given that we are solving a non-convex problem. One of the problems of that is solved by deep neural networks or neural networks in general is the course of dimensionality. There are many examples of how to explain the course of dimensionality, but one of them I like a lot, well, there is a typo here, is to get the number of directions in a space of a given dimension that is forming angles between 88 and 92 degrees. So in R2, in the plane, we have only two such angles, two such directions. In 3 dimensions, there are 3 directions that fulfill that condition. But on D dimensions, this number explodes and goes to e to the D. So when you have, let's say, 10 million parameters, and then you modify the value of one of the weights, you are almost sure moving in a direction that is orthogonal to the rest of directions. Okay, so moving in this, so high dimensional spaces are really hard to grasp, and very, very strange things happen when you go to high dimensionality. One of the reasons, I mean, there are some people trying to understand why we can train neural networks and why they work and why they often work in the same way. One of the reasons why neural networks work is that all minima that you can find in the loss functions are essentially equivalent. And this is a very nice example of once you detect, for instance, in the loss functions of, I think it was a 10 million parameter neural network, you find 2 different minima. You can always find a path through the loss landscape that connects these 2 minima with which is almost flat. So there is practically no change in the loss function. So if you just do a linear interpolation between the 2 solutions, you find this line here. So the path, you increase the loss function, so they are not solutions to your problem. But you can always find a path like this one in which the loss function is almost flat. So this means that all minima you can find in when training a neural network are equivalent. So you can either fall here or fall here, and the neural network the network will work the same. So the predictions will be essentially the same. Another reason why we can train deep neural networks and we can train networks with 1 million parameters or more than that with just a few examples is the fact that the stochastic gradient descent, the one in which we train using noisy estimates of the gradient, is in fact a very strong regularizer. So imagine you are trying to find the minimum of this function, which is just a noisy loss function. If you try to do that using the standard gradient descent, every time you start, you will find a different minimum, which is just the local minimum close to the original place of, to the starting place. Okay, you can do two things. You can convolve the loss function with some kernel, like here, and then with this convolve with this smooth version of the loss function, then you can apply gradient descent, and then you will find the correct minimum. But stochastic gradient descent is doing that for free when we are training a neural network, and it's just producing stochastic changes of the position of the optimum, so that you end up with high probability on a region of low loss. Okay, so in principle, it looks like it seems like the stochastic gradient descent is a very important part of the deep learning revolution. So how we train a neural network using noisy estimation of the gradients is really important. Now we can also, and I'm just close to finishing, we can also now train neural networks without the loss function, without the definition of a loss function. And it's probably you've heard of the concept of reinforcement learning, which is just explaining this scheme. So you have a certain environment that you want to solve. Let's say you want to play this game, and then you have a certain state that can be summarized by just an image of the game, or I don't know, the position of an arm of a robot or things like that. Then you have the state, then you apply a certain neural network. Many times it's just a recurrent neural network that has information of the past. This network produces an action. Then you apply the action to the game and see if you get a reward. So if you manage to do something good or not. And then there are ways to close this loop and start computing derivatives of the weights of the neural network with respect to in other words, derivatives of the reward with respect to the weights of the neural network, so that you are better and better every time you iterate this scheme. And now people have managed to do superhuman players of many Atari games, or I think, or you can, I mean, you probably have seen this this competition between human beings and a machine playing one of these big games in esports, and they are becoming for a much larger number of games. They are now superhuman. Yes. Okay, no question. So that was a summary. If you want, we can go more into the details of some of the parts. And then I just want to drop a few possible projects that might use neural networks. One of them in which we are already working, but and Ivan also showed some results 2 weeks ago, is to carry out 3D inversions of stocks profiles. So the idea is to use neural networks that has as an input the stocks profiles of a 2D field of view, and as an output you get the cube of physical quantities for these very same pixels. I showed in some meetings results with a network like this. I will show results of a network following an encoder-decoder scheme, like the one we use for the multi-frame blind deconvolution. And I mean, there are some problems still during the training and things like that, but this is a Hinode field of view, and these are the velocities, the line of sight velocities for different heights, different iso tau surfaces obtained with the neural network. There are still some artifacts that I mean, we have to solve. This is a work in collaboration with Carlos Diaz and some other people. We also have the estimations of temperatures with height. One of the things that are non-standard when you do inversions with neural networks is that you are not fitting profiles. So if you come from the field of research of inversion codes, then you want to see fits, and you also are sure that your results impose that you are fitting the profile. So your model is fitting the observations. Here we are not imposing that. So later, with this information, we need to synthesize the stock profiles and see if we are fitting the profiles. Okay, this is something we need to do in the following weeks and check that our networks are working properly. One of the advantages of this, by the way, I forgot to mention that this network is trained on snapshots of one single snapshot of 3D simulation of a sunspot by Matthias Rempel. And so then there is a problem of whether the sun and Matthias simulations agree. This is a different issue. One of the things you can also get is the magnetic field in the two horizontal components. They look reasonable, but then we need to check that this is indeed the case when comparing with inversions. But you can also get things like the Wilson depression, the per pixel Wilson depression, so which is the height of every single isotau surface, which is something you cannot get easily from inversions. You cannot get just from inversions. You need to impose something else, and we get this from the neural network, and we also get, in this case, the vertical component of the field. Okay. So another possible project based on neural networks is to do something that is probably interesting for a non-LT inversion, is to carry out inversions without computing response functions. And the idea, I still don't know if it works, but every time you see an inverted profile with a misfit, you sometimes have a guess of which part of the atmosphere you need to change to fit the profile. So if you have a misfit on the wing, you know that you have to touch somehow the temperature in the lower part of the atmosphere to produce a better fit. So based on that, my proposal here is to use reinforcement learning to train a neural network that just with the information from the residuals, and I don't know if from previous time steps, produces a new estimation or a change in the physical quantities that will produce a better fit to the profiles. So just having a look at the residuals. This is an enormous advantage for non-LTE codes because in this case, you would only need to do one single synthesis instead of computing the response functions to every single parameter you have in your model. But I still don't know if this works. So this is just based. This is probably a hope more than a proof of concept. And then something that I think is interesting for things like inversion with helium 1030 and D3 is to use a recent proposal for invertible neural networks. And it's the idea that you can train a neural network that goes from the observation space, in this case Y, to the parameter space, in this case X, by also imposing the forward process. So you want to go from observations to model parameters by also using the same network to synthesize the stocks profiles. This introduces a consistency on the neural network, and this allows, as explained in this paper, this allows people to get a probabilistic inversion problem in which from observations you get an estimation of the probability distribution of the model parameters, taking into account that some information is lost from going to the model parameters to the stocks parameters, okay, in our case. And I think that's all. So yeah, that's all. So maybe we can start discussing. If any one of you has questions or suggestions or things to tell in the group. Or if you want me to go more into details of something.
I have a question,
Yes.
which so it's also related to what I discussed in the previous 2 weeks ago. So yeah, the question is the following. Let's say that we want to do inversions with neural networks. Sorry for this example. And we, for example, train it on a certain set of data. Mm-hmm. That basically means we have found the optimal weights for convolution and densely connected layers in order to describe that data. But what bugs me is that basically with this we are somehow assuming that we are describing all the possible data that we want to interpret, right? Mm-hmm. So we are vastly decreasing the dimensionality of our data.
Yes.
Is that correct?
I don't have an answer for that. I would say there are some arguments in favor of this, that if you have, so you are, you are somehow limiting the flexibility of the stocks profiles you will see from the training set. That probably means that in the inverse process, your network won't be able to extract information from something new. That's true. So my idea here is that probably we need something in cascade, in which first you have a network that detects outliers from the training set, and then everything that is is not an outlier, then you can invert with a neural network, and everything that is an outlier, then you can just probably raise a flag and have a human analyze it. Which is, I mean, what people often do when facing an observation. You just isolate all the outliers, all the profiles that are non-standard, and then you focus on that. And then the rest, you just apply a standard 3-node, 5-node standard inversion. And this gives you the average properties of the field of view.
I had a question. If you go back to your reinforcement learning idea.
This one?
No, at the end, the reinforcement learning. The idea that you had for reinforcement learning.
This one?
Yeah. So I don't quite understand how is this different from what you did on the results you just showed previously? You didn't train on the best fit to the spectrum?
Yeah, but my idea here is that you still can use a synthesis code that can change you can still change the physics of the problem. So you are not, let me restart. When you do what I did in this example here, I have to fix somehow the model. So my idea with reinforcement learning is to train a sufficiently general optimization algorithm that independently of what you put as a forward model, it will fit the profiles. So in some sense, we often use Leverman-Marquardt to do the optimization of the chi-squared when we do an inversion. So fundamentally, it's just having a smarter Marquardt algorithm that does not depend on response functions.
Okay, so you did, when you did previously, did you train? You took a model of a Murim model.
Yes.
And then you trained on columns of the Murim model and spectra or columns in the mirror model. What did you how did you train this?
So this is trained like this. So I get 2D patches from the Muran simulation.
Okay.
2D patches of Stokes profiles. So 4 Stokes profiles, X, Y, and lambda.
Mm-hmm.
And the output are the same patch, same spatial patch, with 7 parameters and at 7 different heights.
Oh, I see. So you're sort of training on a splined version of the atmosphere.
Yeah, exactly. Yes.
So you could, I mean, as we talked about this before, and Ivan has been starting to look at this. You could have your training set be the intensity, the Stokes parameters, and your and train on the actual columns of Muram, right?
Yes, so you can expand this. Instead of 7 heights, you can use the full stratification of the simulation. Yes.
Right, and so then how would that differ from the suggestion you made with the reinforced learning?
Well, in this case, you do 2D patches. So in a single run, so it's an end-to-end approach, but you still depend on the Muran simulations being something close to reality. In the reinforcement learning case I propose, if you train that with sufficient flexible number of models, let's say you use, you want to invert calcium 8542, and then you start trying to change, using Nicole or whatever, or Stick or something like that, or whatever code you want for the non-LTE solution. Right. Then eventually you will end up with an algorithm that can deal with different spectral lines or things like that. So it's more like a meta-learning approach in which you train something that is trained to learn or to optimize.
Yeah.
Okay.
So then you allow more flexibility basically in what you're fitting.
Exactly. So and potentially you can train on a few lines, and then if the meta learning technique is sufficiently general, you can just change the spectral line and it should work. Or it would work. I don't know if it should, but
yeah. So you're giving it some insight into what it's trying to fit in the spectrum.
Yeah, exactly.
Or what it has to change in order to fit the spectrum.
Exactly. So my intention is that the meta-learning algorithm learns that if you have a misfit on the core of the line, then you have to touch the temperature and velocities on this height on the atmosphere.
But if you try to enumerate those number of learning, strategies, or there are a fairly small number of meta learning strategies, right? I mean, is there going to be sufficient? Do you anticipate there'd be sufficient constraint that the machine can actually learn?
I don't know.
Yeah,
I don't know. That's a proposal. I don't know if it will work. My first idea was to try with LTE inversions and see if it works, because then I have access to the response functions, and then I can use standard training techniques for that. And if it works, ideally you should extend that to non-LTE, which is very time consuming.
Yeah, it's interesting.
Any additional comment or?
Well, I have a very important comment, and that is that we need the next speaker. So we need to volunteer for the 2 weeks from now.
Yeah.
It can even be 1 week from now if the person insists, although it doesn't smell that way. So yeah, if nobody approaches us until this time next week, I will have to poke you with a stick. I mean, you, like plural you. And yeah, Andres will put this online, and we will share it on the mailing list, so you can also share it with people who are not here.
Yeah. Yes. Okay. Any volunteer? Okay. I think you probably need the stick.
Yeah, we will. But I mean, we can also discuss this online later on.
Okay. Anything? I mean, anything that we want to? Anything additional?
Maybe it would be a good idea to start thinking about sharing some learning resources, because I think that there are people who would like to try to do something on their own, but are a little bit maybe scared with this. So I think if maybe we could come up, let's say, with neural network approach to, let's say, Milne Eddington inversions and something super basic for image deconvolution or something like that, like some really toy problems that maybe a few of us could prepare, and we can also look at each other's codes and make sure that notation and everything is consistent so that people can follow it easily. Yeah. And then we can put it online. Maybe it would be a good learning repository for something like this.
Okay, great. Yeah, we can discuss this online and then make a few examples, something simple.
Yeah.
I'm wondering if anybody has experience. I'm quite interested in figuring out what the machine is learning. So again, so in this reinforcement learning, you sort of wanted this meta strategy of to tell the machine what to learn on. But the flip side of that problem, to actually just train it and then ask what is it picking out of the spectrum, is interesting. And I'm wondering if anybody has any experience in like unwrapping the learning and figuring out what's the most important aspects of the training that are coming through once you're done, right?
Yeah, I don't have experience, but I've read a few papers about this, trying to see, trying to watch inside the network and trying to see what's interesting for some. I mean, for instance, computing a response functions of the output with respect to something inside, and I can try to share some of these results.
That would be great. Or if you could send some references also ahead of time, that would be good too.
Yeah. Okay. Okay, so it looks like we finished. Ivan, anything additional?
We don't. Anybody has questions here in Göttingen? No. No. Okay. Pradeep just proposed that we could think about implementing some of these examples in SSW package.
Okay.
So, or something like that. So.
Great.
Yeah. Anyway.
Okay.
Okay. Yeah. See everybody online, and yeah, approach me if you want to give a talk.
Thanks very much, Andres.
Great. Thank you.
Thank you. Bye.
Bye.
Bye. Huh? If you will, he is large.
Yeah. True.
What is
the talk was great. Everybody was super happy. I'm leaving now, and we talk online.
Okay.
Bye.